Welcome and thanks for joining us.
My guest today, Jim Blankenhorn, Senior Vice President of Environment and Security at Amentum.
Jim, it's good to have you with us.
Oh, it's great to be here. Thank you.
And let's talk about the energy and the energy infrastructure in the United States. This is a huge topic right now. And just from a simple, maybe engineering standpoint or physical vulnerability standpoint, what is the state of our energy infrastructure right now? It's pretty vulnerable, isn't it?
I think when we talk about energy infrastructure, we're talking about we need to talk about the entire value chain. So we start with the mining and the drilling operations. We go through the fuel fabrication and conditioning. We go through the power generation, storage, transmission, and ultimately the end user, the customer end user. The American Society of Civil Engineers routinely grades out infrastructure within the United States. And the last report card they did on energy infrastructure, they actually graded out some of the components of the infrastructure at about a C-. And the reason for that was because some of those components have reached their 50-year design life. And so that represents a number of vulnerabilities. There's physical vulnerabilities, or the vulnerability of physical failures. There's the vulnerability associated with IT failures, and then there's the vulnerability associated with cyber attacks on that infrastructure.
Got it. So that means that a lot of the pieces have been in place a long time. I know the GAO recently had a report talking about large-size power reduction transformers, things that are the size of a small bus maybe.
Right.
Some of them are 50 years old sitting there, and it's hard to source replacement parts for some of that old infrastructure too.
Absolutely.
So there might even be a supply chain part of the whole infrastructure question.
Yeah, I mean, I think industry has done a fantastic job in maintaining our energy infrastructure. Remember, we've been on a carbon-based energy infrastructure for over a century, and it has served our nation well through all of our growth and prosperity. But as you mentioned, there are components of it that are dated, they are aged, and that represents risk and vulnerabilities to the environment.
Now, as someone who remembers the great blackout of 1965, I also remember this is the event that led to the creation of the regional reliability councils, and a lot of thought about how to update the middle of the last century to update the reliability. What about the reliability, resiliency of the energy infrastructure? Maybe that kind of effort of the 60s and 70s maybe needs a refresh too, sounds like.
Yeah, when we talk about energy infrastructure, there's a lot of common terms that are used to describe the requirements, the expectations. So things like, when we talk about energy, we talk about affordability, we talk about sustainability, we talk about dependability, and redundancy, and we also talk about reliability and resilience. So when we're talking about reliability, what we're really talking about is the ability of the system to meet the demand on call. And when we talk about resiliency, what we're talking about is the system's ability to weather or to survive process upsets and interruptions. So whether that's from physical failures or IT failures or other demand failures that cause the system to be unreliable. And so those how we describe those two terms. When we look at some of the federal agencies, Department of Defense as an example, their solution, or one of their solutions that they're looking at to address reliability and resilience, is to create microgrids and to create unique infrastructure on their bases and installations. And they're doing that so that they can ensure uninterrupted power supplies to perform the DoD's critical missions. They're also looking at some of that infrastructure being remote and transportable and deployable to forward operating bases, forward deployed to overseas installations And they're doing that again to remove the reliance on local energy infrastructure, which is prone to interruption and contamination.
Now, if you are a facility and you have your own microgrid, that's a big change in how it's been done. You're just a member of the grid that serves everybody else. But maybe there's an advantage to the older model. That is, if something happens locally, then there's this vast enterprise that can reallocate and re-switch and redirect power sources such that a local problem can be served. But if you're on your own disconnected microgrid and something happens, you're out of luck.
Yeah, the term independent or islandable is certainly, it's in its strictest, truest form, it represents some liabilities and vulnerabilities. I think going forward, while that is certainly a goal, I think what we're going to see, though, is still that integration between a number of different networks that can support each other. So we're going to have to build redundancy into these systems as we go forward.
All right, and then the renewable energy is a big question, for the United States, and it seems like there's a lot of maturing that has to happen. I mean, even if you look at the windmills, you ever see one of those generators in the hub of the propeller, on the ground? They're huge.
Yeah.
To hoist a thing like that up by the thousands into the air just seems like not all that efficient. So talk about the renewable energy question and how where those technologies can mature to where they can match the reliability and growth and capacity that we've had for so many decades, as you mentioned, under the carbon-based system.
So I think you're hitting on a couple of different topics that have a lot of intersection. So we hear a lot about clean energy. It's a topic globally. We also hear about climate change, and there's a lot of intersection with those two topics, given that the outcomes and the requirements are very similar. So let me take you back a bit and start with the Paris Climate Accords. So the Paris Climate Accords were signed by 194 members of the United Nations Climate Committee, including the United States. And what the accord does is it establishes a framework to allow each one of the signatories to develop their own plans, their milestones, their goals and objectives to achieve carbon neutrality. So the overall goal of the climate accord is to limit the mean temperature change to less than 2 degrees Celsius within the 21st century. And the models that have been run show that in order to do that, we have to reduce greenhouse gas emissions by about 50% in the next decade, and by about 100% or go to carbon neutrality by 2050, meaning that we are removing as much greenhouse gas emissions and CO2 from the environment as we're putting in over a standard period of time. In the United States, then, when we look at our energy infrastructure, about 90% of our greenhouse gas emissions and our CO2 emissions, let's start with greenhouse gas emissions, come from energy production and come from the consumer usage. About 75% of CO2 emissions come from those same sources. So the U.S. has established a goal of being carbon neutral by 2050. And so all of our federal agencies now have developed strategic plans, and they've developed plans, implementation plans, goals and objectives. And what they consist of is a number of near-term, mid-term, and long-term implementation plans. And so that's driving technology development, and it's driving technology development in those sustainable renewable energy sources you're referring to, with wind and solar and thermal and hydro. They're also driving they're driving hydrogen clean energy. How do we efficiently and safely generate, store, convert, transport the hydrogen as a fuel source? They're driving initiatives in technology development in reactor space, nuclear space. So we're seeing next generation reactors and small modular reactors being invested in heavily. And then we're seeing a lot of investment in technologies associated with batteries and battery storage, transmission. As an example, the wind industry, one of the biggest challenges to that is the high percentage of energy that we lose just in transmission compared to what's generated before it gets to the end user. So a lot of technology developments being driven by these climate change initiatives that we've established both within the United States and then globally.
Yeah, that's interesting. You mentioned these small and modular types of reactors. The National Nuclear Security Administration and the NRC, they're looking for talent that can come in so that they can have the staff they need to understand this new technology of reactors, because they're not just miniature 3-mile islands, they're totally new technology.
Right.
And this is coming on.
Yeah, the small modular reactor concept, so the Department of Energy, as you mentioned, the NRC, and Department of Defense, they're all looking for, again, back to this islandable, independent energy source that can service local areas or regional areas. And so instead of building the large nuclear reactors that we've seen in the past, they're looking for these more scalable, flexible, small modular reactors that can provide power on demand, like I said, to specific areas. So there's a lot of technology development going into those areas.
And what are you seeing in Congress to try to maybe further this? I mean, there's lots of subsidies that have been voted in for certain industries, but that doesn't seem to really get at the long-term problem of creating a market that is going to go after these new sources because it's economical and because it's efficient and because there's a payoff in it.
Yeah, so I think the transition or the evolution of our energy infrastructure, it does require an investment in development, in deployment, in demonstration technologies, and all of that comes at a pretty high cost. And so we need investment strategies, and we need offsets and subsidies to, at least during the transition phase and then into operations, we need to be able to control the cost, because ultimately those costs get shared with the rate holders. So what's happened here just in the last couple of years, 2 significant landmark acts have been passed: the Bipartisan Infrastructure Law and the Inflation Reduction Act. And these 2 acts have placed hundreds of billions of dollars into initiatives and incentives, subsidies, grants, tax write-offs, and offsets. The Bipartisan Infrastructure Law, as an example, is primarily focused on rebuilding the infrastructure for the country. And it's focused on developing the technologies and then deploying the technologies, and in a manner that accelerates the transition to a carbon neutral economy. The Department of Energy is significant in this regard, in terms of they are the administrators for the funds available through the Bipartisan Infrastructure Law. And they've got a couple of their own initiatives that they're championing that is designed to incentivize and accelerate industries' development and deployment of clean energy technologies, both at local areas but then in regional areas as well.
All right. And I want to go back to hydrogen, because I'm intrigued by that idea. I mean, it's not a new idea. There has been hydrogen in the economy and for different industrial purposes for a long time. But as a power generating source or as an automotive source, maybe hydrogen locomotives or cars and this kind of thing, what is going on there and what is needed? Because it seems like that infrastructure is a little bit behind maybe the wind and solar and some of the others.
So those same legislative acts that we just talked about have a number of initiatives that they are funding and that they are incentivizing. It starts with the microgrid technology. So there's incentives to develop the the controlling element, the element that you have to have at the center of any energy infrastructure that can manage the power generation, can manage the energy storage, and then can manage the transmission and distribution of energy to the end users. One of the other initiatives within those acts is hydrogen energy, clean energy. And in that regard, they're incentivizing industry to develop the hydrogen producers, the hydrogen consumers, and then the infrastructure associated with hydrogen as an energy source. So when we look at producers, some of the things that they're looking at is taking our traditional power generation infrastructure and equipping them with additional technologies like electrolysis systems that use the available power to electrolyze primarily water, produce hydrogen as a fuel. That fuel then needs to be stored or converted to either liquid or solid forms. And then the end user community needs to be developed. So whether that's vehicles, cars, ships, even aircraft, or whether that's other end users that for hydrogen power. Other initiatives include carbon capture. So there's a number of technologies that are being investigated for capturing and sequestering carbon emissions at the source. And then we talked about initiatives in the nuclear space with next-gen reactors and small modular reactors. And then again, there's initiatives to support storage, batteries. We hear about a new battery technology, it seems like about once a month, where someone's had a breakthrough on efficiencies or outputs or materials of construction. And then another area that's a little bit longer term, but there is still investments going in that regard, is in fusion technology. So let's see, November this time last year, and then again this past summer, I think in the May-June timeframe, the National Ignition Facility at the Lawrence Livermore National Lab, twice now they have demonstrated energy breakthrough. So more energy was produced from the target, from the reaction, than was put into the reaction. Right. Huge scientific breakthrough. And now it's back to industry now to figure out how to bring that technology to market. So
that's more like quantum computing. The theory is known, but to get to 100,000 qubits could be 50 years till there's any practical way, because it requires supercooling. Same thing with these energy collider types of things. To have any practical application enough to light up a light bulb, we're not quite there yet.
We're not quite there. We demonstrated the technology, and now it's time. Now it's time for industry to really put their technology development machines to work and to be able to bring this to market. And I'm not forecasting anything, but there are a number of folks that have expressed that we could see fusion in the marketplace in the next 15 to 20 years. So.
All right, well, let's hope so.
Let's hope so.
Just a final question on the grid itself, the wires. What is the status of that? And there needs to be some investment in the delivery infrastructure to whatever the generation source is, correct?
Yeah, I think, and I think that's one of the components that the report card that the ASME did. They graded the transmission systems out at probably a C-, was one of the lower scores. And we talked a little bit about wind being one of the challenges for wind and solar is the transmission. So that is certainly an area with technology development is in high gear. Industry is looking at a number of different ways to improve the efficiency of transmission. There's also an intersection there with storage, right? So how do we develop better storage capacities, more efficient storage capacities tied with more efficient transmission systems to bring and upgrade the current infrastructure?
All right, well, great. Some good thoughts. We thank you for being with us today.
I'd like to thank today's guest. Jim Blankenhorn is the Senior Vice President of Environment and Security at Amentum.
I'm Federal Drive host Tom Temin. For more on this discussion, please visit federalnewsnetwork.com and search Amentum.